We're going to work with matrices a lot, so there are some basic operations that we're going to use. We're going to talk about scalar multiplication. So scalar multiplication is where you put a number in front of a matrix and distribute that number to every single one of the entries of the matrix. So as something very simple and basic, if I were to say 2A and 2 is the matrix 1, 2, 3, 4, we're going to distribute that 2 into each element and multiply it. So we'll get 2, 4, 6, and 8. The other important operation that we're going to have is addition. So when we have matrix addition, we're going to be talking about two matrices, A and B. They have to have the same dimensions, the same number of rows and columns. If they don't have the same number of rows and columns, you cannot add them. And the definition is going to be, we simply add them entry by entry. So we'll have A11 plus B11, A12 plus B12, all the way down to the very end. And because I'm lazy, I'm not going to write them all out. If I give you two matrices, this matrix is a 2 by 3 matrix, so I can only add it to another matrix of the same dimensions. So for example, this is another 2 by 3 matrix. I just go ahead and I add them entry by entry. I have a 1. The next one, I'll have 2, 4, 5, 5, and 6. So for example, let's compute A minus 5i. A is the matrix 9, 1, negative 8, and 7. Then 5i is just going to be 5 bunches of the identity matrix. So if I put these two concepts together, 9, negative 1, negative 8, 7, subtract 5 into the 2 by 2 identity matrix. So we'll get 9 minus 5 in that top entry, negative 1 minus 0, negative 8 minus 0, and 7 minus 5. We'll end up with 4, negative 1, negative 8, and 2. So doing matrix algebra with scaling and addition is pretty straightforward. Matrix multiplication is more complicated. How do I multiply two matrices? We're just going to use this notation, A, B written beside each other. Now that we've got this concept of matrix vector product, we can use it to get matrix product. I'm assuming that when I multiply two matrices together, they're going to give me another matrix. To see what that's going to turn out to give me, let's say B is a matrix. I'm going to pretend it has P columns. So let's say that B is N by P. And then I'm going to talk about what happens if I go B times X. In order for me to be able to do that, I need to have the number of entries in X match the number of columns. By the definition from earlier, that's going to give me X1, B1, all the way down to XP, BP. Now I'm going to take a matrix and multiply it by BX. By linearity, this is going to give me X1, B1, XP, BP. Each one of these columns, each one of these B's has to live in Rn. They have n entries. Let's use linearity over here. So I can go like this. A times X1, B1, all the way down to A, XP, BP. I can use linearity again and take out all these x's. They're all constants. A, B1, down to XP, A, BP. I have to make sure that all these dimensions are consistent in order for these things to be defined. The BI's all live in Rn. That means there are n entries, something 1, something 2, all the way down to something n. That means matrix A, no matter what it's doing in the first thing, it has to have n columns because these two need to match. So we're going to say that the matrix is m by n just to keep it general. If that's the case, this line right here, by definition of a matrix vector product, ABX is going to be AB1, AB2, all the way down to ABP, X1, all the way down to XP. The definition of a matrix product, I'm going to associate each of these columns with this final matrix. Here's what has to happen. A has to be an m by n matrix. B has to be an n by p matrix. The number here has to match the number there. And if I write AB, it's going to turn out to be AB1, AB2, ABN. This is a conceptual definition. When we want to derive results or do proofs or things like that, this is the version that gets used. If you're taking two matrices and you multiply them, it's only going to be possible if these two are the same, and it's going to turn out that your final answer is just whatever happened in the first row here and in the second row there. But if you actually want to sit there and compute a matrix times a matrix, there's a computational version. So here's the definition. If I have a matrix that's m by n, I'm going to write it in terms of its rows, A1 all the way down to AM. And if I have a matrix B that's n by p, I'm going to write it in terms of its columns, B1, BP. Each one of these AIs has n entries, and each one of these BIs also has n entries. And that's perfect. They match, because now here's what I'm going to do. If you want to multiply these two matrices, you're going to think of the one in the front in terms of its rows. You're going to think of the one beside it, the second one, in terms of its columns. You're going to do the dot product version. You're going to take the top row, multiply it by this first column, and your first entry is going to be A1 dotted with B1. Then you're going to move to the second one. Do a dot product there. A1 dotted with B2, and that's going to go all the way down to A1 dotted with the last one. Then you're going to move to the next row and do the same game there. A2 dotted with B1, A2 dotted with B2, all the way down, and that's just going to continue to the very last one. AM dotted with B1, AM dotted with BP. And you're going to get a matrix that's m by p. What I want to do is show you two really important and hopefully illuminating examples. They're going to do multiple things at once. Number one, they'll show you how all this crap works. And number two, they'll bring up a couple of important facts. Example number one, if I say to you, okay, here's a matrix and here's another matrix B. This is 2 by 2. This is 2 by 2. When you multiply them, these two have to match. And then your final answer is just going to be this times this in terms of its dimensions. So your final answer is also going to have to be a 2 by 2 matrix. I'm going to use this computational version just because it's so much more straightforward. The first row goes sideways and does a dot product with that first one there. 2 times 8 is 16 minus 15. I will get a 1. Then I'm going to take that first one and multiply it by the second row. 2 times 4 is 8. Subtract 15. I'll get negative 7. Second row, first column, negative 32 plus 30 gives me a negative 2. And then I'll do the same thing with that second column. I'll get negative 16 plus 30 gives me 14. Just for fun, and because I know you're all very curious people, what would happen if I switch the order around? You say nothing. When I multiply two numbers, the order doesn't matter, right? 5 times 3 is the same as 3 times 5. Unfortunately, matrices are not numbers. Switch them around. Top row times the first column. So I'll get 8 times 2 is 16 minus 4 times 4. It's 0. Right away, I can see that that answer is different than the one I had above. Same thing over here. I'll get negative 24 plus 24. I'll get a 0. On the bottom there, so I'm going to get this next row, and I'm going to multiply it into the first column again. 5 times 2 is 10, minus 5 times 4 is negative 20, so I'm going to get negative 10. And negative 15 plus 30 gives me negative 15. Huge, big, important point. AB is not the same as BA. The order matters. It matters which matrix is on the left, and it matters which matrix is on the right. Another important point is to do with this example. So let's say I give you two matrices. I'm going to do the same idea, dot product version, this into this. I'm going to get 16 minus 16 is 0. Into the next column, I'll get negative 24 plus 24 is 0. Bottom row into this column, 12 minus 12 is 0. And in the final one, I will get 18 negative plus 18 positive is 0. What happened here? If I take two numbers, A times B, the only way those two numbers can multiply to give me 0 is if one of them is 0 or both. But in this particular case, if this is matrix A and this is matrix B, it's possible for two matrices to multiply together to give you 0, but neither one of them is 0. That's so weird. Yeah, matrices are weird. They're not numbers. They have their own little quirks. We're going to define a special matrix operation called matrix transpose. Definition: if I give you an m by n matrix, the transpose of that has the rows and the columns flip-flopped. So the rows of A become the columns of A transpose. Now, as an example here, I've color-coded a 3x2 matrix A, and we take the first column of A and it becomes the first row of A transpose. Second column of A becomes the second row of A transpose. Now, you can see that necessarily the dimensions of A and A transpose can't be the same. The only time they'll ever be the same is when you've got a square matrix. Now, once you've got transpose defined, it's pretty easy to do the usual rules of matrix algebra, adding, subtracting, etc. However, there are some properties that we should mention just for thoroughness sake. Some we'll prove, some we won't. The transpose of a sum ends up being the sum of transposes. If we ever have a scalar multiple of a matrix and we want its transpose, you could think of it sort of on an entry by entry basis, right? If I give you a scalar multiple of a matrix, that means every single entry in that matrix is being scaled by this factor. And if I were to transpose this, you could see that I'm basically just taking that top row and then making it the first column. The point here is that every single entry still has this factor of s, and you could take it out and what you'd be left with is A transpose there. So you can pull a scalar multiple out of a transpose. This one is a little bit more interesting. If we talk about AB transpose, this one is going to benefit greatly from us trying to write things in terms of rows and columns. We could write a matrix in terms of rows. So this matrix can be written like this in terms of its rows. And then this matrix here can be written in terms of its columns. And so when we do a matrix multiplication, what we're doing is essentially taking the first row, multiplying by the first column, and then that becomes our entry here, A1 dotted with B1. And this pattern continues all the way down the line, A1 dotted with Bn. And you could continue this for every single entry that you're doing. I want you to make this observation that because we've got a dot product, it doesn't matter which way we write the order of these things. So if I wanted to, I could put the B in the front. Now, why do you care? What difference does it make? It's going to make a difference when we get to this transposition idea. So if I now want to take the transpose of this, I am going to flip the first row, make it into the first column. So I'll have a B1 dotted with A1, and then that'll go down Bn A1. And then this will go across B1 dotted with AM, Bn dotted with AM. Thinking of it this way, we can see that we've got B1 all the way down to Bn over here, multiplying this matrix with column A1 all the way down to column AM. And you can see that if we do this whole idea, top row, first column, that'll get us to this entry, top row, all the way down to the last column, that'll get us to there. And the point of the story here is that this is B transpose times A transpose. So that's an interesting result. Not obvious, needs a little bit of care. You need to put them in opposite order in order to do that.